So let us briefly recapitulate what we have already done. So we were looking at transformation of coordinates, and so we were looking at transformation of coordinates. We assume that a particle is, or an observer is moving in the x direction, and this is the world line of the observer. And we took 2 points. This is the position of the observer denoted by K. Then this is TA, XA. Okay, and let's take another point B. This is TB, XB. So these are the coordinates of the observer as measured from this coordinate system T, X. We also considered an event P whose coordinates are T and X. So this is what we assumed. This is the coordinate of an event as measured from this. And the proper time of this observer is tau, who is moving along this trajectory in the x direction. And what we wrote down was the following. Let this coordinate x of the particle on this trajectory as measured from this coordinate system be a function of tau, proper time of this observer, some function f of tau, and d is h of tau. This is what we had. And then the physics input was that we assumed that this observer is sending light signal to this event P, and this light signal is being reflected back once again to the same observer, and he is receiving that light signal reflected back from this event P at the position B. Okay, so these paths are basically connected by light signals, and if that is the case, then you can immediately write down the following equations: x minus xa, x minus xa, that is equal to c t minus ta. This is one equation. The second equation, so this is the distance that is equal to speed of light multiplied by the time interval that has been elapsed. Then you can write the following: that x minus xb. Once again, this is the distance that is equal to c tb. So since these are connected by light signals, you can write these equations. From these equations, this immediately implies that x minus ct is equal to xa minus cta and x plus ct is equal to xb plus ctb. So these are the two equations that we have derived earlier, and what this says is the following: that it, okay, you can further think, write one more step to get a nice form for these equations. We know that x is equal to f of tau, therefore xa is nothing but f of tau a minus c. T is h of tau, so this is h of tau. Okay, so x minus ct is basically this, and this is xb, so this is f tau b plus c. Okay, So this is what we have already got earlier from this consideration. And the only physics input, if you note, is that these paths are connected by light signals, and that is the way you come. That is the way you get these equations. Okay. So if this is good, you can see all this. Let me just move this part. Now our task is to find some relation. Our main goal is to find relation between x and t with coordinates capital X and capital T. What is capital X and capital T? So let me just draw this side of the board will not come in the coding anyway. So this was T and this was X. Let us keep this diagram here. And this was the trajectory. This is A. This is T comma A comma XA. This is B. This is TB comma XB. This is the event T comma X. Now the thing is that if you remember your special theory of relativity, then if I call this frame as S, in special theory of relativity, what we have is you have another frame S prime, which is moving with uniform velocity with respect to the frame S, right? Here you can consider that this is your frame, okay? Because this is not an inertial frame. This is obviously a non-inertial frame because this is any arbitrary trajectory. So this is your frame S prime, which is moving with respect to the frame S. Obviously, it is a non-inertial frame, and with respect to this frame S prime, you are assigning coordinates to this event P, and those coordinates are nothing but that I have written as X and T. These are the coordinates that you assign to the event P from the non-inertial frame. In general, non-inertial frame, you can assume that non-inertial. You can go to a special case and say that okay, that non-inertial frame is no longer non-inertial; it is inertial. So then you will come back to a special theory of relativity. Okay. So now you have got these equations, and our aim here is to connect these coordinates with these coordinates. That is what we do in special theory of relativity, because we try to connect xt with x prime t prime. Okay. So here that is the thing that we want to do, and in order to proceed, now looking at these equations, you can immediately say that it is reasonable to assign the following coordinates. So x is a little bit tricky. It is nothing but half c. C has to come because of dimensional considerations, and this is tau v minus tau. Why has this been taken as tau v minus tau a? Because tau v is obviously greater than tau a. Therefore, it has to be in that way. And this half factor, I told you in the previous lecture that you can proceed without that half factor also. Everything should come out to be the same. So what I am doing now is, since my aim is to connect these coordinates with these coordinates, and here what we have obtained is we have connected x and t with the proper times. Now we have to get a relation which connects the proper times with the t and x. So if we know that, so that will give you relations of x and t with capital T and x. And that can be immediately done from here. You can just solve these equations simply. And if you solve these equations, I wrote down the solutions in the previous class. Can you just tell me what is tau a? I think tau a is t minus x by c, right?
Yes.
Huh? And tau b is
T plus.
okay. Since you have, these are very reasonable. What you are doing is you are basically connecting the coordinates t and x with the proper times. You are not connecting it with x and t. That is your goal. That is the connection that you want to reach. But t and x, it is quite natural to ascribe this connection with the proper time coordinates. That is quite reasonable. If you do that, then this gets connected to this. And now what we can do is we can straight away put tau A and tau B relations. And that gives you the general connection between x and t and capital X and t. So what we get is x minus ct is equal to f tau A. Tau A is t minus x by c minus c h is and x plus ct is equal to is f tau b, but tau b is this, so this is f t plus x by c plus c h e plus. So we have got the connection. In general, the relations between xt and capital T and capital X is as follows. These are the general relations where the observer is moving along any arbitrary trajectory. You are not aware about what is the functional form of this trajectory. So you have got some general relations. Now what we shall do is we shall specialize, or we had already specialized to a case where this observer that is moving along the x direction is moving with uniform acceleration. Okay, and the uniform acceleration is g. And we wrote down the equation of motion. The equation of motion you can write down immediately. It is g dt mv. So it is only moving along the x direction, so you don't need to put a vector sign. It's a v velocity along the x direction. So d dt mv that is equal to not g. So if you take this, so you replace this now by this m is the relativistic mass. So this relativistic mass is basically m naught times gamma. You put a gamma where gamma you know what that factor is. Gamma is 1 by square root of 1 minus beta square. Beta is b by c. So if you do that, then this will cancel, m naught will cancel, and we solved this equation in the previous class, right? And if we solve this equation, the final relations that we had obtained were the following: c square by t cos hyperbolic tau by c. Any problem? Let me just write down, then I take questions. So c by g sine hyperbolic g tau. So once again we can see that the functional forms that we had assumed in case of an observer moving with an uniform acceleration, the functional forms are these. So that you can calculate problem to problem. If I give you a problem, you can calculate the functional forms. Now, just some interpretation or conceptual issues. What is this velocity v? This velocity v is the velocity of the accelerated observer who is uniformly accelerating as detected by an observer in the inertial frame with inertial coordinates t and x. Okay, who is in the laboratory. And what is dvdt? Same. It's the acceleration of that accelerated observer as measured by this. And what is this uniform acceleration? This uniform acceleration is a bit tricky. It is basically the acceleration in an instantaneous inertial frame where the linear observer is at rest or the accelerated observer is at rest. So that is the uniform acceleration. It is the acceleration in an instantaneous inertial frame where the accelerated observer is at rest. So that is the uniform acceleration g. So what we have obtained from here is we had solved in the previous lecture that these are the functional forms, and now that we know what the functional forms are, you can immediately find. So x of tau, this is nothing but f of tau, and this is nothing but h of tau. So these are the functional nodes. So you can see that the coordinates of this observer as measured from, as detected from the laboratory, these are given in terms of the proper times. But now you want to get it in terms of x and t. That is the thing that we did not do in the previous class. We shall do it now. So it is simple. It is not that difficult. What we shall do is, since you know what x tau is, you just plug it here. You just substitute here, and if you do that, then the first relation that you will get, or you can do one more thing. And write down the general relation. If you add these two equations, then we get twice of x, that will be equal to f t minus x by c minus c. What বাজে একবার দেখো তো? What is the time? Huh? H, and we are adding the equations, so we will get this plus f t plus x by c plus c h t plus x by c. So this we get just by adding these equations, and what we need to do now is we need to put in these forms here. So let us do the calculation and see what we get. By the way, you know what a Minkowski observer is? Minkowski observer is one who is moving with uniform velocity with respect to some inertial frame. And then Rindler observer is one who is moving with uniform acceleration with respect to a inertial or Minkowski observer. Minkowski is basically inertial observer. So that is what Rindler observer is. In general, this observer who is moving along any arbitrary trajectory is not a Rindler observer. Okay. Rindler observer is a special case of that one who is moving with uniform acceleration. Okay. So let us do this calculation. F t minus x by c, so that will be c square by g cos hyperbolic d by c tau. So in place of tau, you have to put t minus x by c minus, then once again c. So c square by g will become common. Take it outside because this c multiplied by this, and we will get sine hyperbolic d by c plus f p plus x by c. So this will be plus h, that is h is sine hyperbolic evaluated at c plus x by c. So what you need to do is calculate this expression. That's it. It is not that difficult to calculate. So this will be equal to c square by g. So this will be, from each of these things you will get twice. So this will be e to the power of g by c e minus x by c plus exponential minus g by c e minus x by c. So this is this term. Okay, e to the x plus e to the minus x minus sine hyperbolic. So this is e to the power of g by c. And then minus, so this will be plus exponential. If I make some error, please tell me. Now this is cos hyperbolic. So once again, this will be to the power of g by c. And if you have some better method of doing this, you are welcome. You can do it in your own way. This is this plus exponential g by c plus x by c. And then the last term e to the power of so there should be some cancellations now. So you can immediately see that this term cancels this term, and this term cancels with this term, and there should be another cancellation.
Last term.
This will go with this one, right?
No. The next one.
Last and third
The
last.
last time, second time.
Last and
Third last. The next one.
just cancel this. What was this? T plus x by c, right? So last with
The next time.
this one.
Yeah.
So this cancels. So how many terms are there, Ashish? So you have 1, 2, 3, 4 terms. And what we can do further is that we can write this x divided by another 2, so this will be 4. Okay? And now what we can do from here, so e to the power of so e to the power of gx by c is common from each of the terms. You can just get rid of this. Gx by c square. Thank you. Gx by c square, that goes out. This also goes out. Goes out. This one. Okay. So from here you can see that this term and this term adds up, and so is this and this. So you get a 2. So once again this cancels this 2. Once again this becomes 2. And now this is x. Okay. So I've taken this factor. I just get rid of this and get rid of this. So what is this one? So this is twice cos hyperbolic gt by c. So twice 2 gets cancelled. So what we have is the following: e to the power of so x is this. And similarly, by using the other relation, subtracting it, you can calculate the other one also. This will be nothing but C by G. So you have nice relations between the laboratory coordinates and the coordinates of the uniformly accelerating frame. And the coordinates of the uniformly accelerated observer are called or that frame is called the Ringler frame. So Ringler frame coordinates is denoted by the coordinates T and X. And X, T, these are the inertial coordinates. So these are the transformations that we were looking for on the Minkowski or the laboratory frame, inertial frame, and the Ringler frame, uniformly accelerating frame. We started deriving it in the previous class, but we did not finish it. So this is okay. So do you have any questions at this point? Any question? Okay. So let us proceed from here. Now we come. So the calculation part is more or less done. Now you will come into the interesting physics that you can learn from here. It's a very important problem. You can learn a lot of physics from it. So a bit of more calculation, but not much. Let us calculate what this is, Ct minus x. So what you do is just multiply this by c and then subtract this from this one. So you will get c square by g will be common and e to the power of gx by c square will be common, and then we have sine hyperbolic gt by c, and you are subtracting that part. So you have taken these factors out. So cos hyperbolic right? This is what you will get. Okay. So let us simplify this a little bit further. If you simplify this, it will be c square by g to the power of g. This sine hyperbolic, this will be. So from there, we have a factor of 2 outside. E to the power of g by c minus c. And then we have minus the power of gt by c, gt by c, then minus this is what we get. Is it okay? Just a minute. Did I write it correctly? E to the power of is correct. If it is correct, then okay, so good. But these are very confusing. When you look at these things, it creates a lot of problem. E to the power of g, and you get where the cancellations occur. So these two terms gets cancelled, and from here these two terms add up. So this 2 gets cancelled. Minus.
So it defines that it is a space-like
It is a
space-like separation.
space-like. No, it is. There is no space-like or means everything is causal here. Why are you thinking about space-like or time-like?
Ct minus x has a negative sign overall.
No, that is a different thing. Means you have taken this combination. It has nothing to do with space. You are just, this is algebraic, right? I'm not writing any metric. When you will write the metric, then the question of time like and space like and all those things will come. And this is perfectly causal, so this is completely, so there is no problem with it. Okay, so now you will see that this, you have taken this minus sign out, and this I wrote it down as, okay, so let me just write it. Let me remove this. You know what the transformations are, and therefore you can write this as Ct minus x is equal to minus c square by g to the power of minus g by ct, right? This is what we get. We just check it with my thing. So I have written it down as, I don't know. Okay. So let me, here I have written it down without the minus sign. Okay. Capital X minus this. And similarly, if you calculate this combination, which I am not calculating again, you can do it yourself. So Ct plus x will be from the same equations. You can calculate this to be c square by g to the power of. There is a reason of doing it in this way. Okay. Another thing is that I have missed this factor. Writing down this thing, I missed a crucial factor of e to the power of. No, I have put this down. I have taken it. I have combined it. So that is there. So c square by g. So e to the power of g by c square x plus c. Okay. So if you do this calculation, similarly you will get this. It is e to the c square by g e to the power of g. Fine. Okay. Now a little more algebra, then will come the very nice physics from it, and I can assure you that you will enjoy the physics and see what is really going to happen. These are all very simple algebra. So just wait a little bit more. So you have got these relations. Now let us write down the metric ds square. And ds square is what? We are using the mostly positive signature. So this is c square dt square plus dx square. I am suppressing y and z. Y and z, since it is moving along x direction, you don't need to worry about y and z. It is there. This dy square plus dz square. Forget about it. This you can write it down as dx minus c dt, or with a minus sign. Take out a minus sign, then this will be c dt minus dx and c dt plus dx. This is the line element in the inertial frame. Okay. And what we want to do is we want to express this line element in terms of the regular coordinates t and capital X. This is our aim, and for that we have calculated this. This you can write it in a very nice way. This is nothing but the d operator, the derivative operator, dt minus x. So that is the reason we kept it in that way. It just simplifies the calculations a lot. So this is ct plus x. So you know what ct minus x is and what ct plus x is. You just put it there. That's it. So if you put it there, so this will be ds square is equal to take the derivative. So here is a minus sign, so minus and minus will become plus. So this will be c square by g d of to the power g c square, and then ct plus x, that will be so you need to calculate those things. We don't need these things anymore. This is equal to
So that will be c square, c will not 4 by d square.
It will be, thank you, c to the power 4 by g square. So this is c to the power 4 by g square. And you take the derivative. If you take the derivative, then you will get g from both. I am taking the factors. It will be g square by c to the power 4 derivative of x minus ct, and that will also give a derivative of x plus ct. Okay, then multiplied by the exponentials will remain there. It will be g to the power of g x minus ct by c square and e to the power of g x plus ct by c square. Okay, and from here you can immediately see that this one and this one cancels, right? And so cancels, and therefore you get a nice form now. This will be e to the power of 2gx by c square, and leave this. See, this combination is very nice because you can write this immediately as minus c square ct square plus. See how nice it is. That is why we computed those combinations, ct minus x, ct plus x. You could have done it in a different way, but then you have to do a lot of algebra. But if you look at these combinations, then you get it immediately. Not much algebra, you get this result. So let me now write down this result, because this is a very important result that we have derived. We have to get to one more form, and that we can come in a moment. So this is equal to by the way, our signature is this diagonal. So this is minus okay. So this is the line element that a linear observer will measure of any event, of any two events. So this is the infinitesimal line element measured by a linear observer. So one more step we have to do. We now define a new coordinate, and that coordinate is defined in the following way. See, this is on top, so it does not look nice. So what we shall do is shall define a new coordinate x bar, which is e to the power of gx minus c square. This is what. Okay, so if you do that, if you do this now, you just take a derivative of this. So if you do that, you will get g by c square dx bar, that is equal to g by c square dx e to the power of x. So this cancels on both sides. So you can immediately see that you can write this down as in a very nice way. So this is multiplied by this thing. So this is minus c square e to the power of that factor multiplied by dt square. But this factor is nothing but this. So I will replace it by 1 plus g x bar by c square minus c square. This is this, and this is dt square. That is done. And what we have found out is that dx, this thing, dx multiplied by this thing is dx bar. So that is nothing but.
So there will be a square in the first one.
There will be a
Square, 1 plus g square.
thank you. There will be a square. Very good. There will be a square in the first one. Very good. A second. Just a minute. Minus c square. Eta, and this is the form. I think I have got it correctly. Minus c square. This factor is the square of this, so this is minus dt square, and dx this is dx bar square. So you square it. That will give you dx square, which is 2. So that is 3. Okay.
We could have obtained this form without even considering 1 plus g square by c square. Just g square by c square equals to.
Anyway, whatever choice of coordinate you, but you have to reach to this result by whatever choice system you do. But you should be able to. This is a nice convenient form, as you will see in a moment why. Okay, so our final result in these coordinates, where x bar is related to x in this way, is this. Okay. Do you have any questions? What do you think we should do with this result? Why is this result so important?
So this is nothing but taking x as x bar is a very small approximation.
Right. But this is exact.
I mean, we can.
We could have done that. We could have done that. But there you see, a 2 factor will come. Right? But this result is exact. We have not made any approximation. What you are saying, what George is saying, that is that you can expand this, make an expansion and keep those terms. But we have not made any expansion. We have kept everything exactly. But why is this result so important? That you should be able to say.
Somehow it is curved.
Why? This is okay. This is a good point that Sabu is mentioning. You can already see that your metric is not flat.
Yeah.
Metric is not flat.
Yeah.
If you calculate the curvature, you will get a curvature here. It's a curved spacetime. Because curved spacetime, I told you at the beginning of the lecture that the Minkowski flat eta mu or eta ab, whatever, is diagonal this, and we are using the mostly positive signature that we have. So we have this, and in the curved spacetime, these are not constants. So you can see that this is not a constant. This is the metric is actually dependent on the spacetime coordinate, on the spatial coordinate in this case. So this is one thing. But
So
then
we take derivatives of the metric, and we can get the form. I mean, if we take some others, then we can get the Newtonian form.
that is also good. That is a good point. You are good. You should get back the Newtonian result from here also. That is fine. We shall talk about the Newtonian limit later on. But why is this result important? This result is very important. First of all, you can see that if you take this uniformly accelerating observer, then the metric as measured from the point of view of the uniformly accelerating observer, that is a curved metric. That is fine. But now comes the most important thing in general relativity, and what is that? Huh? I told you in the previous class that is the equivalence principle.
Yeah.
That is the most general thing. See, whatever thing in physics, if you have a principle in hand and if you follow that principle, everything should follow. Now apply the most important principle in general relativity, and that is the equivalence principle. Equivalence principle says what? It basically says that if you are in a arbitrary gravitational field, locally you can construct or direct a locally inertial coordinate system where the laws of physics or laws of nature will obey those of special relativity, as in an unaccelerated frame, right? So, my way of understanding is that you will not get this anywhere. Just very simple thing. So, general relativity means uniform gravitational field or arbitrary gravitational field, freely falling elevator. Then what is happening? Gravitational field, freely falling elevator. Just think of Earth, acceleration due to gravity, uniform acceleration due to gravity, freely falling elevator. What happens locally? No gravity. So acceleration due to gravity, you can quote unquote minus freely falling elevator is equal to special theory of relativity. Special theory of relativity means what? G is 0. So in this quote unquote equation, uniform gravitational field minus elevator, freely falling elevator is equal to 0 gravity. Quote unquote equation. So uniform gravitational field is equal to freely falling elevator. And that elevator is falling with uniform acceleration, at least in an instantaneous inertial frame. Okay, so this is a quote unquote equation. So what does that tell you? Uniform gravitational field is equal to freely falling elevator with an uniform acceleration g. So whatever is happening in this problem, by the equivalence principle, it will happen in a uniform gravitational field also. So here what we had. Here we had there was no gravity, flat space time, uniformly accelerating observer. By this quote unquote equation, the same thing is now this Tx frame, this is no longer inertial. This is what? This is in a uniform gravitational field. Uniform gravitational field. An elevator that is freely falling. In the elevator there is no gravity, right? It is uniformly, but locally there is no gravity, right? So this problem, when you turn back by the equivalence principle, you go back to these coordinates t comma x. In that t comma x, now you assume that there is a uniform gravitational field. So like us, we have p and x, and Gangopadhyay is sitting here, and he is in a uniform gravitational field. And Gangopadhyay's teacher is also standing here. He is also in a uniform gravitational field. What are their coordinates? T comma x. And their line element, you can never write it to be a flat space-time coordinates. What it should be? It should be ds square. You should at least replace it by c square 1 plus gx by c square whole square dt square plus dx square. So in a uniform gravitational field, this was uniformly accelerated observer. By equivalence principle, in a uniform gravitational field, when I am sitting here in a uniform gravitational field. So this is Earth, and this is this. In these coordinates, the metric should be this by equivalence principle. And you can see obviously if you calculate, so this is a curved space-time. Why curved? Because there is something called curvature which we shall come later. We shall calculate. So this is something very important. You should keep this in mind. This dt is the time interval. This, what is this dt? Dt is my clock, and I'm looking at a event p. Okay, and this is the time interval dt measured by my clock in a uniform gravitational field. And if I go back to those coordinates t and x, that will be flat. But d capital T will be the time interval measured by uniformly accelerating in a freely falling elevator in the absence of gravitational field. So what it basically says is that you could have derived it from a different way also. This result could have been derived in a different way. That also we can do. It's a completely different. You can start from this problem and you can derive directly, try to derive this result. That what will be my metric in a uniform gravitational field. You can derive it directly. But what we have done a trick. We have taken the help of Einstein's equivalence principle and we have converted this problem to an equivalent problem where there is no gravitational field and the observer is moving with uniform acceleration. And that we can do by that quote-unquote equation. And from there we calculated that metric, which is this. Now you apply equivalence principle, write the metric in a uniform gravitational field. But this you can derive it in a different way also.
But sir, if we take any other coordinate transformation other than that x prime to x, we could have got a different result. How can you say this is correct and that is wrong?
See, the thing is that by some coordinate change, you are able to come to this form, right? Now you will say, okay, this is a matter of coordinate change, right? Coordinate change. But that is what I am saying. You can derive this result from a completely different way without using anything. Uniform, how did we derive this result? By considering the uniformly accelerated observer. But this you can derive it from a different way.
Physically,
Now
how
accept.
can
This result, when you get to this result, now you see that okay, you got this result. So this must be correct. Because these are two different approaches of getting the same result. Into different approach, okay, you are getting the same result. So then that must be correct. Okay. Good. Okay. So let me just repeat the equivalence principle once more. Experiments in a sufficiently small, freely falling elevator for a sufficiently short period of time will give results which are indistinguishable from those of the same experiments carried out in an inertial frame or in an unaccelerated reference frame in empty space. This is the principle of equivalence. You look at this result and keep this result in your hand. We have got it. We have got the what should be the metric in a uniform gravitational field. Keep this result at hand. Let us now look at how clocks will run in a uniform gravitational field. How will clocks run? Now this is a third approach you can say. So if you get the same result from there, then you are sure that this must be correct, right? Or that must be correct. So I'm giving you a third approach, and this is a very nice approach. So how will clocks behave? So let me just consider that. Let me first draw a nice structure. So you will see, I was very happy to see the structure because you'll see that very nice. We learned something from here. So this is a simple. I think my diagram is not that good, but you can understand this structure that you will see. And this is an engineering feat that you should appreciate. Even if you learn general relativity, you should appreciate this engineering feat. Because you know, when you want to put up rockets, rocket must have a very nice launching pad from where it should go up. And there is a lot of engineering there, so you should appreciate engineers also. See, it is attached here. And what happens when you get the thrust, this particular thing, this particular structure is called a truss. This is a space truss. So these structures are called space trusses. And this is attached to this part. This part opens up and then it goes up. It's a very nice structure that you have in rockets. And here, assume that you have a person sitting over here with some clock. And here, you assume that you have this person sitting here with some clock. And now comes some quantum information notation or whatever language to call this A, and call this B, and this is Alice and this is Bob. So you have quantum information also here. You have Alice and Bob. Okay. The problem is very simple. This rocket, obviously, this is attached to the surface of the Earth. So this is in some uniform gravitational field G. Okay. And now what is happening is that this person Alice and this Bob, their height difference is h. Okay. Fine. Manjuri, ठीक है जी तब? Good. This person is sending signals at at some intervals of time. Okay. So at time t is equal to 0, he has sent a signal. Okay. And that signal has some frequency, say some omega. Okay. What do you expect to happen in a uniform gravitational field? How can you address this question? So at time t is equal to 0, he has sent a signal, and this guy, Bob, has received the signal at time t is equal to t1, say. Okay? And then at time t is equal to delta tau a, so he is giving signals at intervals delta tau a. And this Bob has received the same signal after T1 plus delta tau b. So the rate at which he is sending the signals, he is not receiving the signals at the same rate. You can see, or the time interval at which he is sending the signals, he is not getting the signals at the same time interval. You could have taken this to be delta tau a, taken it to be the same, and see what would have happened. You can do that. I will do it. In fact, I will do it. But let us assume in general that this is delta tau b. In simple words, at time t is equal to 0, he has sent a signal, and after 2 seconds, he has sent another signal. When he has sent this signal, say after 1 microsecond, he has received the signal. He has sent it after 2 seconds. Question is, will he receive the second signal after 1 microsecond plus 2 seconds? Or will the difference be small or large? That is the question. Is the problem clear? Suppose he has sent some signal after 2 seconds, he is also receiving after every 2 seconds, he is getting the signal. Now, what do you expect? Will it be in a uniform gravitational field? Will he receive the same signal after 2 seconds? After, say, the time interval will remain the same or no? But in my calculation, what I shall do, I shall keep it to be different. You will see why. Otherwise, we will land up to an inconsistency. Is the problem clear to everyone? Is it clear? If it is clear, so let us do the calculation and see what happens. So you will see that once again, in a uniform gravitational field, you know what the metric is. We have just now derived it, right? We wrote it down. You could have done the calculation from this metric also, but we will not do that. We will do it in a different way. What we shall do? We shall apply the equivalence principle. So what is the equivalence principle? What is happening to the rocket in a uniform gravitational field? The same thing will happen to the rocket in the absence of any gravitational field, and the rocket is uniformly accelerating with g. So now I am considering the same rocket with Alice and Bob. This is just for your reference thing. So Alice is sitting here with his clock, and Bob is here. This is A, and this is B. So he is now uniformly accelerating upwards. Okay?
Sir, you have not considered any gravitational field here.
Gravitational field Dhurini. I have not tried to understand why I have not taken any gravitational field. Equivalent means uniform gravitational field minus elevator is equal to zero gravity. Quote unquote, roughly would. Uniform gravitational field is equal to freely falling elevator, which is uniformly accelerating. Zero gravity and with uniform acceleration. Okay. So you have this. So this same problem by equivalence principle, by EP, we have this. Look at this problem. Now I am assuming that the rocket is uniformly accelerating and it is far from any source of gravitation. So let me write down what the position of ZT is, of Bob at time t is. What will be his position? By simple Newtonian mechanics, it will be half gt square. Okay. Okay. One comment here before doing the calculation is something very important. What do once again, as I asked you repeatedly, what do you expect? Since this problem is by equivalence principle is the same as this problem, so he is sending signals, say at intervals of 2 seconds. But since the rocket is uniformly accelerating, he will catch up those signals earlier, right? From here, because he is moving up. This is so you can roughly expect this thing to happen. So what it basically means, the rate at which he receives those signals will be more. This is what you expect without doing any calculation. Let's see what happens when we do the calculation. What will be the coordinate of ZAT of Alice? This will be nothing but half gt square after a time t, obviously. After a time t. This will be half gt square plus h, because this height difference is h.
In this equation, this time t, that time with which respect?
Oh, this time you are measuring with, you are fixing some coordinate system. Just go back to that problem.
In which way?
Yes,
In a S frame, inertial frame, সেখান থেকে tx দেখছো.
But sir, in that case, how can we say that the Newtonian law can be applied?
You're assuming this. If you do it without Newtonian law, you get the same result. Because you will make approximations. This is the simplest scenario. There was no need for me to do it in this way. But you will see that you will get a very nice, elegant result, and that will be easier to understand. See, the calculation that I have done, if you show it to a class 8 boy, he will not be able to understand. You are able to understand. But this, if you show, you will understand everything. Because this, he knows this. He knows this. Half ft square. So ZB at time t is moving up in g. Half gt square, that he knows. This we learn in class 8. And what will be ZAT? Half gt square plus h, because difference is this. There is no problem with him. But you are right. There is a word of caution whether these equations will hold or not. We are assuming that the acceleration is not acceleration due to gravity is 9.8 meter per second square, and the time of interval that we are considering is not so much that you have reached the relativistic regime. You are still in non-relativistic regime. Then these things will work. Okay. So now with these equations, let us calculate the distance traveled by the first pulse. The distance traveled by the first pulse. So what will be the distance traveled by the first pulse? This will be, just see the sign. The sign is quite important. So let me just remind you, at time t is equal to 0, he has sent the first pulse. Alice has sent the first pulse. So the distance traveled by the first pulse will be z0, and he is receiving, Bob is receiving the first pulse at time t is equal to t1. What is the position of Bob at time t is equal to t1? Zb t1. So distance traveled by the first pulse is Za at time t is equal to 0 minus Zb at time t is equal to t1. Right? And that is equal to what? Very simple. Sending light signal. So they are connected by light paths. So that is C T1 is the first equation. What is Za at 0? Look at these equations. Za at 0 is H. And what is Zb at T1? Minus half the time. Because this clock, my clock somehow is getting slow.
That is fast.
Huh?
Ultra fast.
Every 10 minutes I see that my clock is running slow. Is it because of general relativity? No. I think it is slow by 1 minute, or the strange effect that is happening from today. This is the first equation. And now this is the distance traveled by the first pulse. Distance traveled by the second pulse, what will be that distance?
Tau A minus ZB1 plus tau B.
So the second pulse, Alice has sent the second pulse at delta tau A interval. So at that time his position was Za delta tau A and minus Zb. What is the time after which he receives? Bob receives T1 plus delta tau B. And that is equal to what?
C T1 plus delta tau B.
C. Very good. T1
Plus delta tau B minus delta tau B.
very good. Minus delta tau A. Let us use these equations. So if you Za tau A, delta tau A, this will be what? H plus half this minus Zb. Zb, this is half G T1 square, and that is equal to C1 T1
C1.
sorry. Okay. This term we shall neglect. It's very small. Because we are assuming that he is sending signals. We could keep that term, but we are assuming that that term is very small, so neglect it. Similarly, delta tau B will be also very small because we shall calculate numbers later. And if you assume that this is small, then what you will get is nothing but this will be T1 square plus 2T1. Okay, so this is an approximation that we make, and you also have the following: H minus half GT1 square, that is equal to CT1. Use this is our equation 2, right? Now use equation 1. If you use equation 1, we will see that H minus half GT1 square, that is equal to CT1, because it's the first equation. So if you use that equation, then these terms will cancel. Okay? And therefore, the final equation that you get is C delta tau B minus delta tau A. So actually you can see that we have not used any calculus, neither we have used any special theory of relativity, nothing. We are just using Newtonian mechanics. And no calculus, no integration, no differentiation, nothing. And you will get a very nice result from here. So this will be C delta tau B minus delta tau A, and that is equal to, obviously there are approximations here, we get minus G T1 delta tau B. It's a very nice equation that you get. Now you can immediately see that had I assumed that delta tau B, the time interval after which Bob receives the signal sent by Alice, is the same as delta tau A, then what would have happened? If delta tau B is equal to delta tau A, then this is 0. That would imply that G is 0. So there is no gravitational field. That is, but we are considering a problem where there is gravitational field. So you are forced, if G is non-zero, you are forced to take delta tau B to be different from delta tau A. There is no other way. Okay. From this nice equation, you can take this on the other side, and we can write this as C plus GT1, that is multiplied by delta tau B, is equal to C delta tau A. And therefore, you will get delta tau B is approximately equal to, because this factor will go down, and then I will make a binomial expansion. So you can take this C outside by C, C and C cancels. So this factor goes down, and you assume that GT1 by C is small. The time interval after which Bob receives the first signal, that is something such that G multiplied by T1 by C is small. Okay. So if you do that, then you can make a nice binomial expansion. You will see that this is, it becomes GT1 by C times delta A. So what it says is that if you are in a uniform gravitational field, then Bob will receive the signals at shorter intervals of time because of this factor. This is a factor which is less than 1. From the first equation, what we had, H minus, just take the first equation, H minus half GT1 square is equal to CT1. GT1 square is also small. So roughly, H is approximately CT1. Right? Replace T1 by H by C. So we get H. Can you see some similarity of that factor? 1 plus Gx by C square with this? You can see some similarity. Right? You are having that same thing, but now with a minus sign. If you take that to that side, it will become a plus sign.
So T1 is being replaced by H by C.
T1 is being replaced by h by c from the first equation. So what it tells you, this is a nice equation. From here you can write. So the inverse of this is the rate at which Bob receives the signals sent by Alice. Inverse of this will be approximately, let me write equal to now 1 plus, because this will be inverse, h square. So this is the frequency, the rate at which Bob receives the signals sent by Alice, who is sitting on the top. So once again, this we did in the rocket uniformly accelerating with g, right? But again, back to equivalence principle. This is the same result as what you will find in the problem, that structure that I drew. It was the problem of a rocket sitting in a uniform gravitational field. So Alice is sending signals from the top, and Bob is receiving the signals at the bottom. So what does this result tell you? This result tells us that this guy, this Bob, who is sitting at a lower gravitational potential, here is the physics, listen very carefully. With this guy who is sitting at a lower gravitational potential will see the clock of the person who is sitting as a higher gravitational potential run fast. Run fast. And the guy, Alice, who is sitting on the top, will see the clock of the guy of Bob, who is sitting at the lower gravitational potential, and run slow. Run slow. And this effect is called the gravitational time dilation effect. This is the gravitational time dilation. You should be very excited to see this result. It's a beautiful result in general relativity. And we have not done much actually. We have not learned Einstein equation also. Only one principle. And you can see everything is coming out very nicely. So the guy in gravity, it tells you that the guy who is sitting at a lower potential, gravitational potential, you see the clock of the guy who is sitting at a higher gravitational potential run fast. And vice versa. How is this effect different from the time dilation effect in special theory of relativity?
Both will see the same effect in ST.
Both will see the same frame of difference. And here we use S and S prime frame.
And time dilation.
No, the SF uniform velocity moving.
From one frame, if the time seems slower, from the other frame, it will also seem slower.
Correct. From one frame, but partial answer, not total answer. This is partial answer. In special theory of relativity, time dilation, both the observers will see the other observer's clock run slow. Run slow. But there is one more point, crucial point. The crucial point is that here, the two observers, gravitational time dilation effect, they are at rest with respect to each other. They are not moving. They are just sitting in a uniform gravitational field. They are sitting. Special theory of relativity, they can move with respect to each other with two inertial observers who is moving. যদি চুপ করে এক জায়গায় বসে থাকে তাহলে কিছুই হবে না, nothing will happen. In the same inertial frame, no effect, right? One is moving with respect to another. So that is the crucial point. One is seeing the other's clock run slow, but in what way? When the one guy is moving with respect to the other guy with uniform velocity. That is special theory of relativity. Two inertial frames which are connected by boost with a non-trivial boost, means non-zero velocity, right? So that is special theory of relativity time dilation effect. Here in gravitational time dilation effect, there is no motion among the two guys. Both are sitting with respect to each other, at rest with respect to each other. The whole effect is occurring due to a gravitational field. This is the gravitational time dilation. This is something very important. Okay. Now let us do some number crunching. Let us do some. This is called back of the envelope calculation. You can just do it in the back of an envelope. So if your supervisor tells you that do some calculation, just go and calculate it in some piece of paper at the back. So and you will get a nice order of magnitude. And what is this back of the calculation envelope calculation? Suppose there are two theorists who is sitting, two theoretical physicists. For example, consider me and Monoranjan. The height difference is not much because it's just 10 feet. But let us consider that I am sitting here and Monoranjan is sitting on the top. And how much top? So let us just calculate it, give an order of estimate. Suppose it is 30 meters. Okay, 30 meter in feet. Do you have an idea? Can you say quickly? 30 but kotala 90 feet কে বলেছে 90 feet তাহলে কতলা 9 তলা 9 তলা 10 তলা উপরে আছে আমি গ্রাউন্ডে আছি ও 10 তলা উপরে বসে আছে যদি আমাদের বিল্ডিংটা 10 তলা নয় 4 তলা so this is 30 meter so this is roughly 90 feet so this is 9 floors. So the heart of a human being can be considered as a clock, right? And it is beating. If I try to measure his with my clock, his heartbeat signals are coming, and I am measuring those signals, his heartbeat signals. So what will I measure? I will see that his clock, his heart is running faster. By what factor? The factor will be 1 plus GH by C square. Put in the numbers. Let us put in the numbers. 1 plus 9.8 meter per second square. So this is a dimensionless number. Obviously, it has to be multiplied by 30. We are in SI units. 9.8 meter per second square multiplied by 30 meters divided by speed of light. 3 into 10 to the power of 8 meter per second square. The whole square. Everything is fine. So if you calculate this number, this will come out to be, this will be 1. So you see the effect due to gravity is 10 to the power of minus 14. Very, very small. Very small. So over a period of 100 years, what will happen is that his age will be more than my age by 10 by 1 microsecond. You just calculate 100 years how many seconds are there. So this is the factor 10 to the power minus 14. So over a period of 100 years, Monoranjan will, if he sits at 30 meters above, he will be older than me by 1 microsecond. And that is not much. 1 microsecond over a period of 100 years. So both of us will be gone. And 1 microsecond over a period of 100 years is nothing. So he is just older by. So that is a very small price because at 30 meter high, he will be having a very nice view from the top, which I will not have. At the cost of 1 microsecond over 100 years, he is enjoying that nice view. And by the way, 100 years, we shall not live 100 years, maybe another, say, maximum 40 years, and then we are gone. So you can see that this general relativistic effect, the gravitational time dilation effect, is actually there, but it can be very small. But this effect can be large in case of other kind of objects. And let us do that calculation. The light emitted from the surface of a star. And let us assume that star is a white dwarf. You know what white dwarfs are? Have you studied this? Who is an astrophysicist here? Ajay, you are doing under Ramakrishna? Devanjan, okay, very good. And he's also astrophysicist, right? So white dwarf, he must be knowing more than me. But white dwarf, roughly speaking, is a compact object, right? Is a compact object. So what do you mean by a compact object? What is the best way to understand what a compact object is?
Density will be high.
Density is very high, so you can just calculate and give an order of magnitude. For example, if you consider our sun, you can see it in Google if you give a search. Our Earth, which is much smaller, has a much smaller mass than our sun. Our Earth radius is roughly 6400 kilometers. Okay, and sun, if you see the radius, it is huge actually. It is in the order of 100,000 or something like that. Maybe 600,000 or maybe 1200,000 kilometers. The radius of the sun. Why dwarfs? Why compact objects? Because this object has the same mass as mass of the order of solar mass, but its radius is 1,000 kilometers or 1,000 meters, something of that order. Let me just see the value. If I have, it's 1,000 kilometers, or it can be smaller than that also. So that is the first compact object. So you can imagine, as she is saying, that the density is very high, very high. So it will have a big gravitational field. So the curvature and everything, you have not learned what curvature is, we shall learn soon, is very high. And the next compact object is what? Is a neutron star. You can imagine objects which have the same mass as that of solar mass, but radius is like maybe few kilometers, 10 kilometers or 20 kilometers. So those are neutron stars, much more denser than white dwarfs. And then comes the giants, the monsters, which are black holes. So let us not worry about, but now I shall show you one thing. We'll see what a black hole is immediately, but without even going to, because in what I feel is that in general relativity, you should be able to understand the concepts very carefully, because it's conceptually quite involved. The calculations are, it's a subject where the calculations are also difficult and concepts are more difficult than calculations. That is why general relativity is very difficult. So let us now see a star, a white dwarf, which is emitting some light signal from its surface, and it is emitting at a frequency omega star. Okay, and this light signal is being measured by an observer who is far away from this white dwarf star.
Inertial observer.
He's far away. Okay. If you have raised this question, this is a good question. Usually, in GR, since this is a very important question actually, inertial or what? In general relativity, measurement of energy is very important. In special theory of relativity, so let me just make a small digression. What is the time? Or the timetable? Because I want to cover a lot. So about, let me see how much I need to cover today. If I'm done, then not much. Okay, I will be able to say. In special theory of relativity, if you recall your special theory of relativity, how do you measure the energy of a particle? In 3+1 dimensions, this is the 4 momentum of the particle. What is the zeroth component of this? E by c is the momentum, really, the vector component, pi. What is I? I runs from 1 to 3. And if you calculate PA, this is a Lorentz invariant. This is equal to the rest mass square of the particle. Okay? And this is the energy of the particle. But in general relativity, you have to be very careful. General relativity is a little problematic. You cannot just say that this is the energy of the particle. In general relativity, you need to really give the energy of the particle. You need to say what the 4 momentum of the particle is and what the 4 velocity of the observer who is measuring the energy is. So the energy of the particle, it is something like this. In general relativity, you have to be careful. Special relativity, okay, energetic particle is this. You don't need to worry. Because in whatever inertial frame, you know, always have this is equal to m square. Okay, so that is not a problem. But to get the energy of the particle in GR, you have to be very careful. You have to specify who is measuring the energy and where is the particle located, where is the observer located. So here, as Manjuri is saying that, I'm saying that the guy who is measuring the signal is far away from this star. So far away, by far away I mean, so practically he is at infinity. At infinity, I will assume that that guy who is measuring this signal frequency is not seeing or is not being affected by the gravity of this guy. So, quote unquote, he is in some inertial frame. He is in the absence of any gravity. And I shall write down one result. You can ask, but this we are just smuggling in some result. What will be the metric of such a star of radius r in the region outside this thing? What will be that? This will be ds square. Let's forget about the other two coordinates. There is a, write it down. Okay. The metric, this is the line element outside for R, where this R is greater than R. This is a line element outside this star. Please don't ask me at this point how do you get to this line element. We shall take this result for the time being, and we shall later try to. This is the Schwarzschild geometry. So you can see that this metric is for this line element or this geometry. You can see that this is curved. You have already seen one example of a curved geometry. So you can now see that this is another example of a curved geometry, and this is a Schwarzschild geometry. So Schwarzschild geometry is basically, just to get you acquainted with, is basically the vacuum solution of spherically symmetric vacuum solution of Einstein's field equations. So you have some dynamical equation in general relativity, and if you solve those equations in vacuum, assume that the metric is spherically symmetric because this is a spherically symmetric star, you will get this kind of a metric. Okay. Just keep this result in hand. We shall come back to this result later. And also keep this thing in mind, that energy, how is it measured in general relativity? It is not only given by the four momentum of the particle whose energy you want to measure. You also need to know the four velocity of the observer who is measuring the energy. That is very important. And this GAP is obviously the complementary. Okay, it is not eta. And further, you can see that if you want to go to the special theory of relativity limit, which I shall go now, you will record the standard result from there. Okay. Let us come back to the previous problem and apply that result that we have obtained earlier for gravitational time dilation. At the surface of the star, what will be the potential? The potential is minus G m by R. Right? This is the potential. And also, if you remember, this result was what? Mu plus mu b 1 plus gh by c square mu b. And what is this gh? This gh you can write it down as delta phi. Right? And what is delta phi? Delta phi is phi A, the potential of at which Alice has minus the potential which Bob has. And that is equal to GH, the gravitational potential in a uniform gravitational field. Now you can see that here also the guy who is at infinity, who is receiving, this is the receiver. Is the receiver, right? He is receiving these signals which are emitted from the surface of the star. So who is at a higher potential? No. The guy who is at infinity. Because his potential is a bound state, no? It's a bound system. His potential is negative, minus gm by r, and this is zero potential. So he is at a higher potential. What do you expect? Higher potential guy will see the clock of the lower potential guy to run slow. So omega infinity will be 1 minus delta phi, that is this gm minus gm by r by c square omega star. So he will receive the signals at a lower rate. So in a given interval of time, he will receive less number of signals. The rate at which he receives the signals will be smaller. So what he will see for the guy who is sitting on the surface of the star and sending signals, the guy who is at infinity, he will see this clock to run slow. And this is once again due to this result. This you can immediately, we have written down from this result that we derived from the simple rocket thing. And rocket thing, as Joyce was complaining that you are using Newtonian mechanics, so the plus point is that you can explain it to kids. If they know S is equal to half ft square and V is equal to ft and all this, so you know, you can explain it without doing anything. So you can see that omega infinity is this thing. And so the guy who will, so this is a signal means a photon. So the photon emitted from the surface of the star has energy omega star. And the same photon, when received there, will have an energy omega infinity. So the energy of the photon that I will measure from the surface of the earth of some distant object will be smaller. So that is what? Energy smaller means it is redshifted. It's not, you're going, energy smaller means you are going to the long wavelength limit, so it is redshifted. So gravitational time dilation that we obtained here is once again the same as gravitational redshift. The time dilation, that was gravitational time dilation, and this is what gravitational redshift. So you have applied the gravitational time dilation equation and you have obtained the gravitational redshift result. This is the redshift result. Okay. Good. Why did I write this result? The question is why did I write this result? The accurate result is this is the actual result. From a very naive calculation without using anything, Einstein equation, nothing. We derived 1 minus gm by rc square omega star. But the accurate result is 1 minus 2 gm by rc square whole to the power of half. That result actually can be obtained from this metric. So try to understand the connections. So which result is correct? Obviously this is the accurate result. But if you calculate the numbers 2 gm by rc square, then you will see that this number is actually less than 1. And therefore, you can make a binomial expansion. If you make a binomial expansion, the first term gives you the thing that I calculated.
ওই রিংলারের যে লাইন এলিমেন্ট ছিল ওখানে তো dx এর স্কয়ারের আগে কোনো কোএফিসিয়েন্ট ছিল না শর্ট সাইডের ক্ষেত্রে যেটা আছে
তো গ্র্যাভিটি ওটা প্রবলেমটা আলাদা ছিল। ওটা প্রবলেমটা ছিল গ্র্যাভিটেশনাল ফিল্ডে মেট্রিকটা কি রকম হবে। আর এটা আরো this is something more complicated and we'll see how you get this metric. The point that I'm making is that this result that I wrote down earlier, that I derived from here, it was what 1 minus gm by rc square mu b omega star. That result I derived it by some very simple arguments without going into Einstein field equation and anything. Accurate result if you go into proper general relativity is this. But then is the first result wrong? No, the first result is not wrong. It is an approximation to this accurate result because if you make a binomial expansion, you get the first 1 minus the result that I wrote down earlier. Good. Any questions? Do you have any questions at this point? Okay. So I shall now try to derive this accurate result from this metric. I am doing some smuggling because I have not derived this result. This result I have told you the physics. This is the metric of a spherically symmetric star outside the star. It is something very similar to electrodynamics, right? You have a source and you want to get the electric field outside the source. So what do you do? You solve Laplace's equation. You have a spherically symmetric conductor sphere and there is some charge distribution and you want to get the electric field outside. So what do? You solve Laplace's equation outside the conductor. So you solve the Poisson equation outside the conductor and Poisson equation outside the conductor is what? Laplace's equation. There is no source. And then what you do? You try to match it with the surface. And the same thing, something similar has been done in GR also. And this metric has been obtained. What I shall show you now is that you can obtain this result, this accurate result from this metric. Okay, this I shall show you now. But before doing that, let me go back to this result once again and let me give you another example. This is a very, very important example. That when was gravitational redshift? So you can see that this gravitational time dilation is nothing but gravitational redshift. If you apply it to the surface of a getting signals from stars. When was this gravitational redshift? And one more thing, this redshift for Earth, for person sitting on the surface of the Earth, this is very small. But you can see that if you put in this number, this gm by r c square, mass is solar mass and r is 1000 kilometers. That number will not be very small. So there is a substantial redshift there, gravitational effect. So you have to take into account that effect. So this is, you can calculate these numbers because I can give you the number. You know what capital G is, m is solar mass, and capital R is 1000 kilometers, and you can calculate what that redshift factor is. So that will not be small. The next point is that when Einstein gave all this, obviously people will want to test it, whether your theory is correct or wrong. So when was this gravitational redshift first detected? The point is that when was it first detected? So historically, there is a bit of history here. There is something very, very important. It's something called Mossbauer effect. Have you heard of this Mossbauer effect? No one. No one have heard about the name. So it has something to do with nuclear physics. And this Mossbauer effect was first found in 1958 by Mossbauer. And he won the Nobel Prize for that because this was a very important phenomenon. And what is this phenomenon? This is basically recoilless nuclear resonance fluorescence. So that is what people in condenser physics, they are always looking at fluorescence, the experimentalist guys. So this is recoilless nuclear resonance fluorescence. So what is being done is the Mossbauer effect. What people do is you have some ion which is in an excited state, atomic, the nuclear thing is in an excited state, and it is embedded in a solid. And this is nuclear resonance fluorescence. So it is, since it is in an excited state, it is emitting gamma radiation. And you have another thing, another same iron. If it is in, so this gamma is coming here, but some amount of energy must have been lost, because when it is emitting, you know, a gun, right? When you shoot, what happens? The gun recoils. What Mossbauer did, he was very clever. He put it in, embedded it in a solid, so that that recoil is not there. So it is emitting gamma. Everything, the recoil is being absorbed by the solid in which it is being embedded. So it is emitting gamma, and there is an iron in ground state. It is absorbing and is getting excited. So this is nuclear resonance fluorescence, and this was observed at the level of nuclear physics. So that is why it was something very important. It is something very important medically also. All these MRI and all these things, these are done on based on these kind of principles. Nuclear NMR and all these things, nuclear magnetic resonance and all these things. So this was the first thing that was developed in 1958 by Mossbauer, and he won the Nobel Prize. And incidentally, I was the one, all of you know, I was the first batch here, and I did my project in Mossbauer spectroscopy in Shah Institute. I had, all of you guys nowadays, if you want to do theory, you do theoretical projects. But I did an experimental project, and I was lucky enough that I got to learn Mossbauer effect there. At that time, I thought that what I'm doing is not important, it's Mossbauer thing. But this was actually very important, because later I came to know that since it was, when it was discovered in 1958, an experiment was performed in 1959, and that experiment is known as Pound and Repka experiment. Pound Repka experiment. It was a famous experiment. Why? This Pound and Repka experiment actually used the Mossbauer effect, which is something to, has nothing to do with gravity, to verify the gravitational redshift experimentally. And immediately when they verified it, it immediately proved that Einstein was completely correct. Whatever he has given is correct, is working. So let us see how it works. So what is being done is, as I told you, that you have some iron, Fe star, is an excited state, and emitting some gamma. Okay. This iron star, how you will get, is a matter of nuclear physics. You will get it from cobalt 57 by nuclear beta decay. By nuclear beta decay, you go to this thing, same thing, this thing. And suppose this experiment was done in Jefferson laboratory, and they were sitting at the lowest point of this Jefferson laboratory. So here this gamma was being emitted, but this is in a gravitational field, right? So what will he see? And there was some guy, some receiver here. So he is at a higher gravitational potential. Here the iron 57, the gamma is here. So here the signals are being emitted. So what will he see? He will see the clock run slow. So he will receive signals at a smaller rate. So from here, something is being emitted. You want to see the nuclear magnetic resonance, right? So you keep here iron in the ground state. Iron in the ground state. If there is nothing known as, or nothing called as gravitational redshift or gravitational time dilation, then what will happen? Gamma will go there, resonance will occur. But they were not able to get any resonance. There was no resonance. Why? Because gravitational redshift is there. So this signal that he receives here, the frequency, this signal is actually smaller. It's redshifted because he's at a higher gravitational potential. So what did Pound and Repka do? They were very clever. They gave a blue shift. This iron, they moved it. They were moving it. They gave a blue shift. This is a Doppler effect to to cancel that. So the signal is actually getting reduced because of gravitational time dilation. So if gravitational time dilation is really there, so if you give a compensating blue shift, then resonance should occur, right? So what is delta omega by omega? What is delta omega by omega? The change in frequency of this gamma by omega. That must be this factor G by c square, and this is what GR, gravitational redshift. Redshift current frequency ta omega hai. And Pound and Redka gave a blue shift, and that is due to Doppler effect. So delta omega by omega Doppler, that will be what? Doppler factor, velocity u by c. Just equate these two. So u by c, h by c square. What is h by c, by the way? It is the time taken by light to cover a distance of h. It is very small actually. So that is why you remember that GT1, those times you were neglecting GT1 square and all those factors. So U is equal to GH by C, and you can get a nice relation here also. U is equal to GH by C. So this you can write it down as H by U is equal to C by G. This has the meaning that, forget about that, you can write it in this way. But this is Doppler, this is GR. Now you calculate this velocity. This is 9.8 meter per second square, and height, the height at which they performed the experiment was 22.5 meters. H was 22.5 meters. The top of the Jefferson laboratory. So this is 9.8 into 22.5 by 3 into 10 to the power of 8. And so everything when you calculate will come in meter per second, because all these are SI units. And if you calculate everything, this will come out to be approximately 7.35. You can just calculate it in calculator. It's going to be minus 7 meter per second. So this is the amount of blue shift or velocity that you need to give. And what Pound and Redka found that by giving this amount of velocity to that thing, the resonance was occurring. And that directly proved gravitational redshift. So you can see that using the principle of nuclear physics is the Morse-Bauer effect is something very, very important. Very, very important. And you should actually go and read what Morse-Bauer effect is. It is beautiful. But this is something to do with nuclear physics. And you are verifying the effects of general theory of relativity in a nuclear physics phenomenon. And this, because there are no other places to verify. How will you verify? On Earth, gravitational time dilation is very, very small. I calculated it for you, 10 to the power minus 14 factor. That is not much. Nowadays, even if you go to Burj Khalifa and do, maybe you will get something, but that will be that is also very small. You can calculate GH by C square for Burj Khalifa. So that will be not much. But here, you can actually test what this gravitational redshift is, what this factor is. It's very small, but you can verify small thing, GH by C square. So this is Jefferson laboratory, height is 22.5 meters. GH by C square is very small. We have calculated it already. But that small effect you are measuring in a small, in a region, in a phenomena which happens at a small length scale, at a very small length scale, and that is nuclear physics domain. And this was done, as I mentioned, in 1958, and this was verified in 1959. This was the first direct evidence that gravitational redshift is there, and Einstein's theory is working. Good. So, do you have any questions at this point?
How did they obtain such a small velocity? Experimentally, it's very challenging.
Experimentally is very challenging. That I cannot tell you, but they did it. Experimentally, it's very challenging. They managed to, and so you can imagine. So it is not that technology has developed today; it was there already. They managed to give such a small velocity. From 1959, you can imagine. 1959 means 60, more than 60 years, 63 years back. So this was done, and at that time, as you correctly point out, that they were able to give such a small velocity to do the experiment, to verify this thing. Their main goal was to, they were looking at taking Mossbauer effect as a tool, but their goal was to verify gravitational time dilation. So they managed to do it, and now in the remaining time, what I shall tell you is how to get this result. How to get this result from the Schwarzschild geometry. So let us do that now. I shall keep one thing for you to do as a homework, and that is from the transformations that I have derived, the general transformations, try to derive the Lorentz transformation. This you should be able to do. Because those are general transformations, so you should get back the Lorentz transformation also.
So if we just put the value G is equal to square, it comes to the matrix ds square is equal to ds square. I mean, the c square d minus c square d square plus dx square is equal to minus c square dt prime square plus dx prime square. So that is our transformation.
Okay, from there also you can do, right? You can do it from there, but this sort of cheating kind of thing.
Yeah.
But I don't want you to do it from there. I want you to do it from the general relations that I wrote down. Okay. You understand? So that x is equal to f.
So there is one.
Huh?
There is one. Small t equals to capital T minus capital X by root 2. And small x equals to
একদম functional form থেকে করো।
functional form টাই তো correct হবে।
হ্যাঁ, functional formটা কি?
Small t.
ওকে, তাহলে তো প্রবলেমটাই সলভ হয়ে যাবে। x is equal to কি ধরেছিলাম? আর t কি ধরেছিলাম? h of tau.
T equals to
f tau টা কি হবে? f tau, what will be f tau?
x minus capital T মানে f of tau ওটা আপনার
শুধু tau এর ফাংশনই হতে হবে কিন্তু নালে হবে না।
cos hyperbolic tau হ্যাঁ
cos hyperbolic flat space বলছি cos hyperbolic
Flat space.
flat space what do you think f tau will be? This is actually what I want to get is I want to derive special theory of relativity. Okay.
CD.
No. Theta.
What is special theory of relativity? Time dilation. The two observers must move with respect to each other, right? So how should that proper time related? Means suppose I have my proper time and you are moving.
1/√1 - 6
Again, lekho. Write it down. Only you can say probably yes. You want to write. So তুমি f tau টা লেখো যেটা সুবিধা হয় লেখো তাহলে ওটাকে গামা টাও বলে এটাকে তুমি গামা টাও করে লেখো
ওটা
প্রথমটা লিখে দিয়েছে correct because that follows from the special theory relativity time dilation so tau is proper time tau must be smaller than t so t is equal to tau gamma tau okay এসে গেছে ঠিকঠাক লিখছো ঠিকই লিখছো correct. Why is this? Because x for a uniformly moving velocity, x is what? Vt, and t is what? Gamma tau. So v gamma tau. So I want you to start from these functional forms and derive the Lorentz transformation. What Joyashree is saying is also correct. You should be able to get it by putting t is equal to 0, but don't do that. Do it from here. So let me come back to the last thing that I want to discuss. So please do it as a homework. Let me write down this result once again, which I wrote down. The energy of a particle with 4 momentum A and 4 velocity is the observer who is measuring the energy in general relativity. And let us see whether we can obtain the special theory of relativity result from here. Okay. So you a observer is gives a data. Okay. So you this is nothing but VA0 data. What is X0? What is dt deta? dt deta এখানে লিখলে না dt deta gamma. This dxi deta di dxi dt di. This is equal to, if I take gamma outside, c here. That's what it is. Okay. Now in flat space time, this is I got it right. This is E observer. Obviously, E observer measured by an observer. The energy of this particle with 4 momentum pa as measured by an observer. So E observer in flat space time is equal to, in flat space time GAB is eta AB. So this is minus eta AB. PA. This is gamma C. Now I will assume that this observer is at rest. 0. Okay. Therefore, what you have is, okay, it's simple. It has only the 0 component. So this is nothing but the 0 0 p0, and the 0 component you have a gamma and a c. Right? ঠিক আছে তো? এটাকে আমি একটু কেটে লিখেছি এভাবে। This is 0. So special component is 0. So it is only the time component. So the time component, you could have written it like this. UV observer. But here only the 0 component exists. So I can just write this to be 0. So this is 0. But eta is diagonal. Therefore this must be also 0. And therefore this must be also 0. By the way, repeated indices are summed over. So this is what we get here, and U0 observer is gamma C. Eta 00, the signature that we are using is -1. So this is 1. And what is P0? V by C, right? Oh, right. Eta 00 is -1, so this is -1. So this is 1. And gamma is 1. Right? Because gamma is 1 by square root 1 minus v square by c square, v is 0. That is what we have taken because the observer is at rest. And therefore, now you can see that P0 is what? That the relation that I wrote, that is E by C. And this is C. C cancels. Which is the result in special theory of relativity. Special theory of relativity, you don't need to worry about this.
So this is not the result in special theory. This is result in special theory where the observer is at rest.
That is what you should do, no? That is what you should do. Today, we thought. Because the invariant is what? Invariant is the relative, is the rest mass. Invariant is rest mass. Okay. This is just I wanted to show you is a digression. And now, if you have enough energy left, then I will just go to the Schwarzschild metric, or maybe we can stop here and take some questions here. Because I want to show the gravitational time dilation result from the Schwarzschild metric. And then that we will do in the next class. So do you have any questions?
So I have one question. When we are talking about clocks and sending signals, so it is basically how we are thinking time as receiving some signal from other observer. But for the local time, is the person really aging slow or aging faster?
If you there is nothing called, you should not say local time, you should be very specific about it. It is proper time. Proper time.
That's what
Proper time, there is no change. But what you will see is that if he is at a higher gravitational potential, then you will see that he will be aging faster. If you are at a lower gravitational potential.
So it is actually just how we are seeing it. It is not actually.
But it is also, it is not completely correct because
Sir, all these are biological process will be slow.
I mean, it means that biological process should run slower. That means time is actually slowing down.
but see, I am not expert in biology.
No, not
That
biology.
I cannot tell you. But the point is, what you will observe about his thing is that he will age faster. Now, whether he is really aging faster or not from his own perspective, that is a separate issue. And he will see that you are aging slower. You are aging slower because you can understand that. But whether the biological clock is also doing the same
I am
thing,
asking this question because sometimes I have seen these articles that when astronauts are coming back from the space, they have aged a bit more than us.
that is what you have calculated. That is an effect, but it is not. See, I cannot tell you about the biology. No. This is these twin paradox and all these things are there, but it is special relativity. But the point is that the main thing is the following: that whether the biological clock from his own perspective, from his proper time, whether really he is aging or not, he should not age, right? He's in his own proper time clock. But what you will see from here is that he will age faster. That is an effect. But whether that effect is really affecting his thing or not, his age or not, that only biology can say. That I cannot tell you. But it is important that this effect is a real effect. This effect is a real effect because you can verify it by a blue shift. Because you think about this age issue, you think these are not that important. You think about this nuclear resonance thing. There, the effect is really there. নাহলে তো otherwise blue shift দিলে ওটা ইয়ে হয়ে যেত না ওটা blue shift হলেই রেজোনেন্সটা হচ্ছে নাহলে হচ্ছে না so there the effect is really there so that is something very important and as I can only say is the following that the thing is that if you are at a lower gravitational potential you will see the guy who is at a higher gravitational potential to age faster you will see due to the gravity effect. That is only what I can say. But really, whether he is really aging, that I cannot tell you. That I am not sure. But it is.
Sir, I am saying this in a sense, suppose that someone is at a top height. So he's seeing that my clock is running slow. When he, suppose now he